สวัสดีครับ Hello, today I'm presenting research by Ganjansahit Thonglek and others on improving resource utilization in data centers using an LSTM-based prediction model or long short-term memory model. This addresses a critical efficiency problem in modern computing infrastructure. Let's start with the introduction. So, data centers power everything from cloud services to AI applications. They must balance cost, performance, and energy efficiently. And resource utilization is how well we use CPU and memory, which is crucial because even small improvements can save millions and reduce carbon footprint. So the core motivation is applications show predictable usage patterns. If we can forecast actual needs instead of relying on user estimates, we can reduce waste while maintaining the performance. So users often over-request CPU and memory, leading to wasted resources. And the researcher got their question that can we predict actual CPU and memory usage to improve the allocation? So let's see the background. These charts show the scale of the problem. So resource managers allocate based on user requests, but there's a huge gap between allocated and used resources. So data centers typically run at low utilization despite huge computing demand. So previous solutions focused on schedulers and container rebalancing, but most only addresses CPU or memory separately, not both together. And let's see the existing approaches. So current solutions include resource sharing schedulers, container rebalancing, and CPU optimization algorithms. So as I've said before, these things have limitations. Most focus on either CPU or memory optimization, not on both. And these graphs on the right from Google's and Alibaba's data centers show that both CPU and memory patterns are important and interconnected. Let's see the motivation for this research. So, applications have predictable usage patterns over time. We can exploit this for better resource prediction. And the challenge is analyzing multivariate time series data with long-term dependencies and noise. Which is suitable for LSTM, which is ideal for this because they capture long-term patterns in sequential data, as shown in this LSTM architecture diagram on the right. And next topic is the methods. So let's start with the dataset and feature selection. So they used Google's cluster usage trace. The data includes normalized CPU cores, memory, disk space, and I/O requests. So they also applied PCA, which is principal component analysis. So they identify these key features, which is requested CPU and memory and used CPU and memory. Next, let's see the job classification. So the researchers categorized jobs into 4 allocation types, which is over-allocated CPU and memory, over-allocated CPU, under-allocated memory, under-allocated CPU, over-allocated memory, and under-allocated CPU and memory. So they found out that 95.95% of jobs were over-allocated for both CPU and memory. And next, let's see the LSTM model design. So their LSTM model has this architecture with multiple layers, as you can see on the right. So I'll explain these briefly. So first layer is the input layer. It receives the 4 key features. The second layer is the first LSTM layer, which learns CPU versus memory relationships. The third layer is second LSTM layer, which learns allocated versus used relationship. And then dense layer to process the patterns. Then the last one is output layer, which predicts optimal CPU and memory allocation. So they tested memory cell sizes of 20, 40, and 60 minutes. Next is the integration with resource manager. So the model integrates directly into data center workflow. So user submits job requests, resource manager collects usage history, then LSTM predicts suitable allocation, and then manager allocates optimized resources. Then let's see the evaluation setup. So as I've said, they used Google's classless scheduler simulator with 80% training and 20% testing data. So they compared LSTM-based versus RNN-based versus baseline resource managers across different memory cell sizes. And next, let's see the CPU utilization results. So it shows significant improvements. LSTM with 60-minute memory cells achieved 10.71 reduction in CPU wastage versus only 3.57% for RNN. And the memory utilization results. So memory results were even more impressive with 47.36% wastage reduction with LSTM. So the prediction stabilized resource allocation much better than baseline and RNN approaches. And let's compare LSTM versus RNN. So across all memory sizes, LSTM consistently outperformed RNN for both CPU and memory. So RNN suffered from fluctuations due to vanishing gradient problems, while LSTM achieved stable long-term predictions. And next is the discussion. So the key findings are LSTM captured long-term workload patterns effectively. So larger memory cells improved accuracy but required longer training time. Predictions fell between requested and reduced resources, avoiding both over and under allocation. And the implications: improved utilization leads to lower costs and greener data centers, while demonstrating deep learning viability for real-world scheduling. And the conclusion. So the research proposed an LSTM-based model achieving 10.71% CPU improvement and 47.36 memory improvement over conventional resource management. And their future work includes real production deployment and explore optimization for training speed and energy cost. And thank you for listening. If anyone has any question, you can leave it in the comment or something. ขอบคุณครับ